Good morning, everyone. My name is Minghui Chen. I'm an assistant professor of nuclear engineering at the University of New Mexico. So today I'm going to talk about the molten salt research in my lab. We just want to give some research highlights and research activities. We do have a department of nuclear energy at the University of New Mexico. We have about 9 tenure track faculty, 2 lecturers, 3 national lab professors, and 3 research professors. We do offer bachelor degree, master degree, and then PhD degree in nuclear engineering. And for master degree, we have 2 concentrations. One is radiation protection engineering, and then the other one is medical physics. In terms of enrollment, so we have about sometimes 70, 80, 90 undergraduate students. Graduate student, we have about 15 master students and about 35 PhD students. So it's good size for nuclear engineering departments though. So in terms of research, we have a broad research area here. As you can see, some faculty doing radiation transport, reactor physics, criticality safety. For me and another professor, we are working on thermohydraulics and safety analysis. And then also we have space, nuclear power, and thermal propulsion. So a lot of things that you can see. For teaching and research facilities, we do have a nuclear reactor either for education and training purpose. We have institution for space and nuclear power studies, and some lab, like for example, my lab is called Advanced Thermohydraulic Laboratory, and some others. So we are very close to Sandia National Lab and then London, so sometimes we can use the facilities. So next one, which is about my lab, I mentioned we have so we have about 10 staff, students, and I have 2 postdocs. One is working on molten salt printed circuit steam generator, and then the other one is working on reactor cavity cooling system for molten salt reactors. I have about currently I have 3 PhD students. One student is working in Sandia. He is working on molten salt corrosion study. And then I have another student working on molten salt pump technology. So then I have another one which is working on stirring engine for microreactors application. I'm going to have another 3 PhD students. I will talk about the project that they will be working on in a minute. About 3, sometimes 4 or 5 undergraduate students working in my lab. So those are kind of brief introduction about the department and my laboratory. So what do we do? So my research mainly focuses on high temperature systems, thermal fluid systems. So for high temperature heat sources, we can consider molten salt reactors, Fluoride-Salt high temperature reactors, high temperature gas cool reactor, very high temperature reactors. So those things that we will consider micro reactors. And then the other one is concentrated solar power. And then the third one, which is the fusion reactor. So we consider the design, testing for the bracket and the first wall structures. Then we also are interested in doing thermal energy storage. So we consider molten salt as an thermal energy storage medium. I'm very interested in the particle side, so trying to get involved in Sandia, the research group on doing particle energy heat transfers. The next one is for the high temperature heat exchangers. So I have a lot of experience with printed circuit heat exchanger. So we will get a little bit into the printed circuit heat exchanger, and then twist to the tube heat exchanger like Catalyst Power is currently using as the intermediate heat exchanger, and then the last one highly coil heat exchanger, which the high temperature gas cooled reactor they typically use highly coil heat exchanger for helium application. Last section, which is for advanced energy conversion. So I'm very interested in the supercritical carbon dioxide energy conversion, and then helium Brayton cycle, as well as the Stirling engine for microreactor application and then space applications. some project that we are currently working on. So one is for the molten salt thermal hydraulics. So we have some project coming 2 weeks ago, and then 2 weeks. So the first one, which is from Office of Nuclear Energy. So we are doing passive heat remove system for molten salt reactors. The second one, which is developing a compact steam generator for molten salt reactor. So then the third one is for the molten salt build experiment to validate NRC tools that can be used for safety analysis for molten salt reactors. And the last one, which currently we are actively working on, is developing and demonstrating demonstration Fluoride-Salt pump bearing and then seal components for molten salt reactors. So those are for molten salt reactors, basically. I do have a project that's supported by the UNM internal funding. So power cycle for advanced reactors. So the first one is developing a high temperature, high pressure helium testing loop for testing components, instrumentation, for high temperature gas cooled reactors. And then the last one, which is the design and analysis of free piston Stirling engine for microreactor application. Okay. So those are some research going on in my lab. And then I'm going to talk about the project that we have been working for 2 years, which is the molten salt pump technology. And then I will kind of briefly talk about the other three projects that just started. So the first one, which is for the development of pump bearing and seal for molten salt primary pump. So pump actually is a very, very important component in a reactor, right? It's like a heart in the system. If the pump fails, then the entire system is done. So pump is a critical component, so we have to solve some challenges that we are facing for the molten salt application. We have some candidates molten salt pump technology. The first one is called Canada Loto magnetic bearing pump. It's very good option for this application because there's no moving part, there's no bearing, and there's no bearing and there's no leakage issue. Okay. This technology is still in the development stage. So it's had a lot of challenges in terms of the temperatures, and then the I think the wall thickness is very important part. So that's one thing. So this is the figure showing kind of Canada Loto molten salt pump. The second one is short shaft pump. So basically we have a very short shaft. And then in this one, the shaft is short, so it has limited temperature limitation there. And then it also requires local shielding from nuclear radiation. Okay. Now the last one, which is long shaft cantilever molten salt pump. Currently, we consider it as the leading candidate. It's favorable for radioactive high temperature application, but it requires, as you can see, it's long shaft, so it requires salt lubricant bearings, and it also requires seal to reduce the potential gas leakage or release from the primary system. So that's the kind of background. So we wanted to focus on the two components, bearing and seals, and then we try to see if we can develop and demonstrate scale bearings and seals for Fluoride-Salt pumps. Excuse me. Some approach and methodology, as you can see, we have 4 tasks for this project. Number 1, number 2, actually basically for the pump bearing seal, using the same methodology. So we do numeric simulation, and then we design a testing facility so we can get experiment data to validate numerical model, and once the model is validated, then we can do more simulation work. So that will be task 1, task 2, and then once the model is validated, we put it in the pump simulation code. So we do the pump simulation, and then we actually do the pump experiment testing, so we can compare the pump model versus the pump simulation. And then once we have that model is validated or verified, then we can do some scalability analysis. So in our laboratory, we are considering 3-inch size, but in actual application, it can go more than 10 or 20-inch size. So we wanted to see this scalability for the prototype designs. For the pump bearing, we consider journal bearing here as our starting point. And for journal bearing, we have 3 ways to do. First one, we're using analytic solution. So this is for the assembly case. Second one, we can add some features on the inner surface, then we have to do the numerical simulation here. So we do the computational fluid dynamics simulation for completed case that we have screws, we have dampers on the inner surface. And then we will do experiments. So for now, I just talk about some analytic simulation work here. Now, the Fluoride-Salt that we consider here is the fiber salt, temperature 1200 Fahrenheit. For journal bearing, as you can see, right now we only consider extra and helical glues. As for dampers, and we will consider in the future work. Battery material here, right now we consider graphite, carbon-carbon composite, and silicon carbide, those things. So we try to get the static performance, and then my student is working on to get the dynamic performance. This is the analytic solution. So we try to get the pressure distribution in the gap. So we have this space is filled with molten salt. So we want to get what is the pressure in the molten salt when the shaft is rotating. Once we have the pressure distribution, then we can get the force, and we can get the friction factor, and then we can do the calculation of applied load or the power loss. So those are things that we will consider. Once we have pressure drop, as you can see from the 2 equations, one is for the long journal bearing, the other one is for short journal bearing. Those analytic solutions can be done or can be achieved through simplifications. So we consider long journal, which is infinitely long, and then for the short journal bearing, which is it's very short. So we got these 2 pressure distribution, and then we do the calculation and compare to the previous experiment data, so which is from Smith's paper. As you can see, it has large discrepancy, right? And the dot points and then these lines, basically it has large discrepancy. So because of this, then we try to do the numerical simulation to see if we can try to improve the modeling part. So we do numerical simulation. We're using star system, which is CFD tools, and then we all this geometric information. As you can see, the boundary condition as well as the mesh. We also did the mesh independent study. So we found that, okay, here it's, say for example, 12 layers of mesh, which is kind of into the plateau here. So we choose 12 layers of mesh, and then we do the simulation for all the work. So we use a prime journal bearing, and then you can see for different azimuth ratio, the simulation is actually in a good, very good agreement with the analytic solution. That means our CFD model is verified. And the next one, we want to do the validation. So typically for CFD simulation, we will need to do the verification and the validation. So for validation, we don't have CFDs, we don't have experiment data using molten salt. So what we do here is we're using data from literature, and it's using engine oil. So we use the same geometric information, we use the same oil property, and then we do the numerical simulation. As you can see, our simulation result, which is star system simulation result, it follows the data really good. So that means our CFD model is validated here. So once we validate it, then we can do a lot of simulation work because we are trusting our CFD models here. So we have come up with some journal bearing with glues inside, and then we do simulation. As you can see, the performance is there. And then we're using a helical glues, which is the third one. It's reduce the pressure there. So that means the power loss is reducing, and it's giving a better performance. You can see the first one, which is the power loss. Power loss, actually, you can see the right line, which is a helical glues. It's showing the best performance because it has less power loss. Same thing for applied load. It's helical glues give us the least applied load. So that's something that we really want. So based on this simulation result, we will do the experiments. So we design a test facility. What you can see here, we have a molten salt tank, which is the reservoir tank, and then we can melt the salt inside. Then we are putting inside this testing molten salt tank. We have 2 gas cylinders, and then there's the loading transfer inside, which we are placing our bearings. Different loading, we can do different testing here. Now, one thing is, looking inside here is we have a gas cylinder. It's giving a pressure inside, and then we can do different loading depending on its pressure. This is the test facility, actually, you can see. Some other experiments that you can see, one is for molten salt spill experiments. It's just started 2 weeks ago. So we will do experiment to get some experiment data to validate NRC tools. And for molten salt reactor, we typically don't see loss of coolant accidents. We call it molten salt spill accident. So in this case, we have molten salt spill from the vessel or spill from the pipe or pump systems. So you can see this, once it's spill is spread, and then it can go to, it will becomes bubbles, and bubble is burst, and then you have aerosols. So we need to consider these things when we do experiments. So because I only have 1 minute, I think. So those are objective, and then some tasks that we will do. So that's for the molten salt spill experiment. I think I have 2 minutes or more. I didn't start from 20, so. I can. You can wrap it up. Okay, yeah, I'm trying to. So, the next one is for compact heat exchanger for concentrated solar power application. It's for molten salt steam generator. So you can see concentrated solar power, tidal power, GE, nitrogen, ultra safely, all using molten salt energy storage, and then they're using steam ranking cycle. So between them, you have to have a steam generator, right, from molten salt to water. So all these things, they are using all these tubing, shared tubing exchanges. Now, what I'm proposing here is to use a printed circuit exchanger to replace all these tubing heat exchanger. And then printed circuit exchanger basically is a plate type heat exchanger with channels that are chemically etching into the plate. And then we do stack them together, so we get a differential bonding block. And then once we had welded headers, then it gives us a complete heat exchanger, right? Some innovative here, you can see we can prevent the freezing. We can have different channel size, different channel shapes, and then that possibly give us a better performance. Now this is based on differential bonding technique, which is very strong connection for plates. Okay. So we did the thermal design, as you can see, for 50 megawatts CSP power, and then these are the performance and then the heat exchanger side. The last one is for the reactor cavity cooling system, which is basically decay heat removal systems. And then for this one, there's 2 types, as you can see. One is air-based, the other one is water-based. And we were choosing, based on calculation, we were choosing one. This project just started 2 weeks ago also. So this is the design stage. We will do the productivity design. And then once we have productivity design, then we can do the dynamic simulation, we can do the multi-physics modeling, and then we can do the scaling down analysis, so we can make the facility in our laboratory and do the experiment. And the last one, which we will do experiments. I think this is the last slide. So we have some capabilities for doing some experiments. The first one is the contact angle machine. We can do pool boring experiments, flow boring experiments. We have molten salt heat transfer facility that you can see on the left-hand side. We also got a very nice machine, which is for temperature and strain measurements. We can get the temperature and the strain less than 1 millimeter. So we are still expanding, so as you can see here. Okay, so that's all. Thank you.
Minghui, thank you so much. That's super exciting work that you're doing, and I'm glad you guys are doing it right here in, watch that water there. Yeah, we went to the Cut Rate Stage Corporation, so they, we only have so much. So would you be willing to answer 1 or 2 questions before the break?
Sure.
Yep.
Back in the 1980s, there was a program of a 5th generation computer, which we thought the Japanese were able to create a computer with human intelligence. So that caused a reaction in the United States to develop Semitech. And Semitech was an organization based in Texas whose mission was to standardize chemicals, process equipment, and tooling for the semiconductor industry to expand our capabilities.
Do you have a question?
My comment is this industry needs the same type of organization in the government to standardize and expand the work of people in universities and government labs.
Very good. Thank you, Robert.
Thank you. Obviously, the pump technology is something important, but I was wondering from your perspective, what are maybe 1 or 2 other major engineering challenges to making a liquid fluoride reactor feasible?
Certainly challenge high temperature is certainly the challenge, because high temperature give the thermal expansion is really something that we have to consider. So in terms of the engineering side. The other was it's operation. So basically, for my experience dealing with the molten salt, we have to deal it very, very careful. It's not just safety issue. It's more than just safety issue. So yeah.
Thank you so much.
Okay. Thank you.
All right. Together.
Yeah. Thank you. Thank you.
University of New Mexico's got a wonderful program, so we're lucky to have these.